All right, let's take a tool around the periodic table. Okay? When we look at the periodic table here, the periodic table we can think about as being broken up into blocks according to the subshell that contains the last element of the last electron in that element. The first two rows on the periodic table, that's called the S block, because all of these elements, electron configurations, end in an S subshell. Everybody in the first column ends with one electron in the S subshell. Second column ends with 2 electrons in the S subshell. Okay? Notice that the row that that element is on corresponds to the shell that holds the outermost electrons. And then you've got the S subshell with 1. Now I want to point out that helium over here could as easily be written over beryllium because it's 1s2. It's kind of an odd duck over here on this side of the periodic table, but we'll talk about why it's placed there in a minute. Okay? Now, in this section of the periodic table, we have what's called the P block. All the elements here have electrons in their outermost shell going at the end of its electron configuration going into a P subshell. 1, P2, P3, P4, P5, P6. So as you notice, the P block is 6 elements wide, and that's because the P subshell can hold 6 elements, or 6 electrons. Okay? And again, they're on row. This is the second row, so I have 2s2, 2p1. Okay? All the way to 2p6. Here in the center of the periodic table, in this indent, we have what's referred to as the D block. All of the elements in here have electron configurations that end in a D subshell. Now, the whole electron configuration is not written in the box, only the stuff kind of at the end. So notice scandium, 4s2, 3d1. Manganese, 4s2, 3d5. Iron, 4s2, 3d6. All the way over to zinc at 4s2, 3d10. Okay? Everything through argon was filled and we added on. Lastly, these kind of 2 orphan lines at the bottom of the periodic table, this is called the F block. And the F block, okay, has electron configurations that end in an F subshell. Now things get a little screwy here in the F block, and that's because the energy levels between D's and F's in some of these things in the F blocks are really close, and it kind of tinkers back and forth a little bit. We're not going to worry a whole lot about the electron configurations down here because they're just weird. Okay? Now, notice that there's a split here. The periodic table really should be opened up one more time and have a second stair step in it for the lanthanides and actinides. But notice it goes 55, 56, 57, 72. The block goes in here. If the world was perfect, this table would be split open right here and this block would go here. But lanthanum, okay, actually the energy is lower if I put the electron in 5D before we put one in the 4F. Same thing for actinide. They're a little bit out of whack. They're not what we would normally predict by Aufbau. Now, a couple other things I want to point out to you. Chromium and molybdenum are exceptions to the Aufbau rule, okay? And it has to do with having unpaired electrons and giving space. So it goes 4s1, 3d5, molybdenum 5s1, 4d5. They're exceptions to the filling rule. We come over here and we look at ruthenium. Notice that it's an exception too, as is copper and silver and gold. Platinum is also an exception. So there are exceptions to our fill from the bottom up rule. And remember, nature is always going to take the lowest energy route possible. It doesn't care at all about our ideas about how things are supposed to work. It does what it wants to do. Okay? Now, the blocks here on the periodic table are very handy to help me write an electron configuration without having to count electrons. Because I can look at something and I know where its electron configuration has to end, and therefore I can fill in up to that point. Now this kind of periodic table is a little bit of a cheat because, you know, the end is already shown for me. You won't have this periodic table when you're taking test 2. You're going to have just a regular periodic table. Let me see if I have just a regular one up here. I don't remember if I put one in. Well, this will be a good one for us to look at. Okay, so this is one where that F block, things are split and put in. So you can see 1s, then 2s through 2p, 3s through 3p, 4s to 3d to 4p. It's another one of those examples of those filling rules. Okay? So let me choose a block here without knowing what the element is and look at its electron configuration. So let's look 1, 2, 3, 4, 5 over on row 4 in the D block. Okay? So if I look at 5 over in the D block, right here, electron configuration would start like the following. Okay? We start 1s2, 2s2, 2p6. That gets me to the end of row 2. 3s2, 3p6 gets me to the end of row 3. And then it's 4s2. That's on the 4th row in the S block. And then 3d, and if I went over 5, I would go 3d5. So that's 10, 25. It should be element number 25. If you look on your periodic table, element number 25 is 5 over in the D block on the 4th row, and it's manganese, Mn. Okay? Now, in class, I would normally stop here and have you do some practice. So I'm going to depend on you guys to do some practice. Okay? It takes lots of practice, and I'm going to make sure that I give you lots of practice on a homework sheet. Let me back this back up here a minute. Okay? Now I want to point out a couple of things here. Again, looking at our periodic table. Okay? When you're looking at the periodic table here, I want you to notice, and this table is in your book, I want you to notice that when I'm coming across the 4th period, when I hit the D block, it's 3D. The D block is always 1 row behind. So if I'm on the 6th row, when I hit the D block, I'm in 5D. If I'm on the 7th row and I hit the D block, I'm in 6D. The F block is always 2 rows behind. So on the 6th row, when I hit the F block, I am at 4F. On the 7th row, when I hit the F block, I'm at 5F. They're always 2 rows behind. The S and the P, those subshells at the end of the electron configuration, are on the row that we're on. The D block is always 1 row behind. The F block is always 2 rows behind. Okay. Now, some other things that we can get when we're looking at the periodic table. A column on the periodic table is called a family or group. A row on the periodic table is called a period. Okay? So columns are called families or groups, and rows are called periods. And besides talking about S block, P block, D block, and F block, we're also going to use the terms main group elements, transition elements, and intertransition elements. Okay? So let's look at what I mean by these designations. Okay, I'm going to have to go back up to that periodic table again. So let's look at the periodic table here. The first 2 columns and the last 6 columns, the S and the P block, combined are what we call our main group elements. Okay? First 2 columns, the last 6, the S and the P block are referred to as main group elements. The D block, these are referred to as transition elements or transition metals. Everything in here is a metal. And the F block, those are referred to as intertransition or intertransition metals. Okay? So these 2, S and P, that's our main group. This is our D block, is called transition metals or transition elements, and the F block is called intertransition. Okay? Now, a couple other things I want to point out to you about the periodic table at this point. I want you to notice this big dark black line. Okay? That's kind of a demarcation point between 2 parts of the periodic table. There is the portion of the periodic table to the left of the stair step. Those are all metals. Notice that metals make up most of the elements on the periodic table. Elements above and to the right of the stair step, these are called nonmetals. I know, it's really creative naming. Okay? Along the stair step, we find some very confused elements that aren't quite sure whether they're a metal or a non-metal, and we refer to those as metalloids. If you look at the periodic table in the front of your textbook, it points out the metalloids in purple. So boron, silicon, germanium, arsenic, antimony, tellurium, astatine, and this TS element, which I don't remember the name of because it's been newly named, are all considered to be metalloids. Metalloids are somewhere between a metal and a non-metal. They share properties of both. Okay? Metals have some general characteristics in common. They have a tendency to be solids at room temperature. They have high melting points and high boiling points. They'll conduct electricity, they'll conduct heat, and they're workable, which means that I can stretch them out into wires, I can hammer them into sheets. We go with the nonmetals. The nonmetals, portions of them are gases. A large majority of them are gases at room temperature. Okay, oxygen, fluorine, neon, chlorine, bromine, krypton, xenon, radon, nitrogen are all gases at room temperature. So about half, okay? They have a tendency to be insulators, which means they don't conduct heat or electricity. They have a tendency, if they're in their solid state, to be brittle, which means that if I tried to pull them into a wire or hammer them out into a sheet, they would shatter. And that, so they're brittle, they won't conduct electricity, a lot of them are gases at room temperature. So they have very different properties in general, the generalized properties from the metals. The metalloids, they have low melting points, low boiling points, relative speaking. The metalloids like silicon, germanium, arsenic, antimony, tellurium, astatine, they have a mixture of properties. Metals have a tendency usually to be shiny. Non-metals that are solid are dull. Silicon is shiny, like a metal, but its conductive properties are somewhere in between. Under certain circumstances, it'll conduct. Under other circumstances, it won't. You can't hammer silicon out into a sheet. It shatters. It's very brittle, like a non-metal. So those things along the stair step have a mixture of properties of metals and non-metals. They're kind of like a liger, a cross between a lion and a tiger, or a mule, which is a cross between a horse and a donkey. It's got some properties of both. Okay, so they're mixtures. So our periodic table. All right. Let's scroll on down here. Now, I want to talk about electron configurations for ions for a second. Okay? And I want to talk about excited state versus ground state. So we're going to look at an ion first, and then we're going to talk about ground state versus excited state. Now remember, an ion is a charged particle. So the number of protons does not equal the number of electrons. And we have two options here. A number of protons can be greater than our number of electrons, and our number of protons can be less than our number of electrons. Protons greater, that's a cation. Protons less, that's an anion. Okay? Cations are formed by losing electrons. Anions are formed by gaining electrons. So if I looked at a calcium atom, calcium has, remember, the 20 electrons. So it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So that's 10, 20 electrons. Calcium forms a calcium 2+ ion. We'll talk about why later, okay? So if I take 2 electrons away from the electron configuration of calcium, I'm going to take off the 4s2. So its electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6. Okay? Now, if I form an anion, it's going to pick up electrons. So let's look at the electron configuration of oxygen and the oxygen 2- ion. Oxygen has 8 electrons. So it's 1s2, 2s2, 2p, let's see, that's 1s2, 2s2, that's 4, 2p4. Okay? An oxide ion, an oxygen that's picked up 2 electrons, now has 10 electrons. So that's 1s2, 2s2, 2p6. Okay? So the atom, the ion. I just wanted you to see an ion's electron configuration. Now, for atoms, we can talk about ground state, okay? And we can talk about excited state. A ground state atom is when all the electrons in the atom are in the lowest energy position possible, okay? But we can excite an atom, and when we excite an atom, the electrons jump to higher energy shells. So they're not in their lowest energy position possible. Now, when we did the lights and line spectra lab, you were looking at excited atoms. And when those electrons jump out to those higher energy states, it's very unstable. They don't want to be there. They want to be in ground state. So the electrons, after they get jumped out, will fall back down to a lower position, and when they fall back down, that's when the light was given off that you saw in the line spectra. Okay? So let's look at some ground state versus an excited state. If I were to look, let's say, at boron. Boron has the 5 electrons. So in ground state, it would be 1s2, 2s2, 2p1. That would be a ground state. In an excited state, at least one of those electrons is not going to be in the lowest energy position available for it. So it could look something like this. 1s2, 2s1, 2p2. This is not filled, and there are electrons out here. This would be an excited state. Okay, a nice excited state. Or you could see something like this. 1s2, 2s2, 3s1. The 2p is completely empty, and I have an electron out in 3s. Both of these would be examples of an excited state for boron. So if you're looking for an excited state, you want to look at your electron configuration that you're given, and you want to make sure that for ground state, everything's full before you move off to the next orbital up in energy. And if you have one that's not full and you've got electrons beyond that, or you've got an orbital, a subshell completely missing, then you've got an excited state. So ground state, excited state. Okay? Now, when we look at electrons in an atom, well, I tell you what, this is a perfect place for me to end this lecture, and I will pick it up here next lecture.